Hello, my name is Neora, and this is my library report for Lab 6 Magnetic Molasses of Physics 2212. Video contents are as shown on the screen: introduction, related concepts, experiment, computer model, and discussion. The purpose of this lab was to explore the interaction between the falling magnet and the aluminum foil tube using concepts of magnetic induction and eddy current, and to recreate it using a computational model. The results: experimentally measured time the time of falling was 1.246 seconds, while the computationally simulated time was 0.217 seconds. And here is a preview of the experiment. The left image is the computational model simulation, and the right image is the corresponding graph generated by the computational model. Related concepts include Biot-Savart law, which is a formula of magnetic field generated by a constant current; Newton's second law, which is F equals m times a, and it means force needed to move an object is proportional to its mass; and finally Faraday's law, which means magnetic field or flux change is leading to electromotive force. The experiment as you can see in the right image. The system was the bar magnet and the aluminum foil tube, and the surroundings were everything else. Procedures: the foil tube was set up vertically, the magnet was dropped through the tube, and the time it takes to completely fall was measured using a phone timer. And the results is as you can see here. There were 5 trials in total, and the 5 trials averaged 1.246 seconds for the magnet to fall through the tube. And then after the actual experiment, we moved to GlowScript coding system to computationally recreate and simulate this experiment. Here is the code that you can see, and as you can see here, the mu magnitude was used from the experimental value we gained from lab 4, and it was 0.8211 ampere times meter squared. And here is the results. As you've seen in the preview, the left image is the computational simulation, and the right image is the graph of the velocity versus time of the magnet falling. And the time in tube in seconds, so the time it took to completely fall, was, as explained, 0.217 seconds. And 0.217 seconds is quite different from the experimental value of 1.246 seconds. The possible sources of error for this result includes human errors, such as wrongly measuring the time and other tiny mistakes; noise caused by nearby magnetic, electronic, ferrous materials, so basically interception of the magnetic field; and finally, uneven width and radius of aluminum foil could have been the problem, because in the computational model we assumed a perfect cylinder-shaped aluminum foil tube, while in real life it was not quite that. Discussion: what if the resistivity of the conductor were 0? The smaller the resistivity is, the larger the electric current in the tube. This would lead to increased force generated working on the magnet, and it would lead to it falling even slower or not at all if the resistivity is absolutely 0 and the electromotive force cancels out the gravity. What if holes or slots were cut into the tube? The holes or slots would function as nuisance, so it would reduce or decrease the magnitude of the current, and therefore, by Faraday's law, the force acting on the magnet would decrease, which yields a opposite result from the previous question. Conclusion: successfully carried out the experiment and recreated in computational model. However, experimental and simulational values varied, and we identified the possible sources of error for this variance. Thank you.